Well, howdy. So I probably won't go ahead and do anything with the editing like I did on the last one, but I will record this in Audacity so I have a second track and stuff like that, just in case I do need to in the future. If anybody actually listens to these, then I'll probably go ahead and do that later on. But right now it looks like people are listening to about the first 1.3 minutes or so, which means you're just about ready to leave right now. So what I'd like to do is I'd like to do an example that has something to do with stability. So you've got some stability problems on your WebAssign homework. So I'd like to talk a little bit about that here. You should be able to get that from the previous Walter Lewin lecture, from lecture the lecture that went with 13, I think, instead of 14, which is this one. So I think this is a all right problem to do that with. It's a variant of a problem that I often give as a homework problem, as a group homework problem. So what I'm going to look at is I'm going to have a block of mass m, right? And it's going to be sliding along a rail without friction. And this will be in the x direction. So it's going to have a rail coming around like this. There'll be a slider like that. There's a real name through it, but I can't remember it today. And then that's going to be powered by springs, like this, attached to some wall. So this is the center line there. And then it'll come out some distance x here. These guys have an equilibrium distance of L. And then we've got a separation S between the walls. So what I'd like to do is I'd like to push this block from here to here on the other side. So what will be going on here is that the block has got two equilibrium points. One here, X. As long as I've got those, I shouldn't try that because what'll happen. So let's see. Right, I get to change colors if I want to. One equilibrium point here. I thought I changed colors. And one equilibrium point over here, and equidistant to the other side. And you're going to have to push through to get to the other side because the distance between these two walls is less than twice the length of the spring. So what would happen is if this was greater than the length of the spring, or of the two springs together, then the springs would just be pulling and the equilibrium point would be right there. So actually we could take as a function of S the separation where the equilibrium points are if we'd like to. So let's say that's X, and if this is 2L right there, then I really hope I can get another color. Okay, let's hope I got another color here. Can I get a wider line? I'm not sure what each one of these is, so I won't play with it. Okay, it's not letting me get another color. So anyways, if the separation is longer than those two L points, then this point in the center is the equilibrium. However, if the separation is closer than 2L, then what will happen is your stable equilibria will come out like that, right? So you'll have a stable one in the negative direction, your x minus, and a stable one in the positive x direction, that's your x plus. So either way, this would be equilibrium. So if I had less stuff over there, this point here with the slider is a place where it would just stay all by itself, and then if that's true, then there'd be another spot over here that's a place it would just stay by itself. So if you just put it there, it would sit there. And then right in the middle here, this spot, put dots there. At that spot, that is an unstable equilibrium. So you could just barely position these sliders, or this slider, so that it's sitting right there on the equilibrium, that it's right there. But if it goes just a little bit off, right, if it's just a little bit off over here, it would go over here. If it's just a little bit off, it'll go over there. And it's quite unstable. With the springs, it's quite unstable. You need a lot of friction between the rail and the springs to keep it there. This is, in a way, a very simple model of buckling, right? So if I had a common way that people do buckling is if you have a bar, a beam, you want to see how much pressure it can handle before it buckles, you put your force down here. You could do an equal force on the other side, or just put floor or something down at the bottom. And then eventually you'll get to a point where something will happen and it'll flip out over here this way, because you keep putting more and more force on the beam, compressing it more and more, putting more and more strain on the beam. And the beam just can't handle that forever. So that's one way of doing these things. So these are stable equilibria, and these are unstable equilibrium in the middle. That means that if you're farther out than this, right, it's always going to go towards this red line, and same thing here. And then when you're in the center here, it's unstable, so if you're a little bit off, it'll go towards the thick red line. If you're just a little bit off from the dashed line or the dotted line, it'll go that other way. So that's what we're looking at. It's a fairly common problem in engineering when something like this happens. So what I'd like to do, however, is not figure out what these are. Actually, you can figure those out geometrically, which is unfortunate, which is why I'm not asking the problem anymore. What I would like to do is I would like to hit this block with a hammer or something like that. So I'll put a little hammer in there. And if I hit that block with a hammer, bam, I want to make it go fast, really quickly. I want it to start going fast. I want to figure out what the speed is, so it'll get over this bump and go from this equilibrium spot to that equilibrium spot. Now, if you've only got this potential energy, if you've only got this conservative force, so if you've only got the spring force, then it'll go over and then it'll come back and it'll go over and back and over and back, over and over and over again. But if there's any friction at all in the system, then it'll lose energy along the way. And if you've just gotten over the minimum there, then it'll bring down around this other equilibrium spot. So I want to figure out exactly how much energy goes into that, right? Or exactly how fast you have to hit how fast you have to make the slider go so that the block goes from one end to the other and gets to the other equilibrium. It's actually a common problem if you're using the energy instead. So let's see what else we can do. I've actually gotten a little bit ahead of myself. Why don't I clean this up a little bit first? So let's just clean up that drawing so that it looks like it originally did. So I've got my fasteners for the springs there, and I've got my block there, and then I have my springs, and I'm going to want to hit it with a velocity v. So this is going to be what I just called x plus. This equilibrium spot here is going to be called x0. We already know what it is. It's going to be 0, but we're going to actually prove that coming up. Let's see. Is there anything else I should do? I should say that this is S. That's separation. And that's probably it. That's probably it. So that should be sufficient for that. The rest of the setup, what we need to do, we need the givens and finds. What else are we given? Well, let's see. The objects we have are springs. And what do we know about the springs? They have an equilibrium length L and a stiffness K. This is still too small to get all those things in. I'm sorry. It's just the size of the tablet and how well this thing writes on it. What else do I need? Well, I've got a slider. What did I call that? I called it a block. And it's probably got a mass. Let me see. It has a mass M. And what else? I've got these walls. And there's a separation S. And what we want to find is the initial speed to get over the wall. All right, initial speed V. Okay, so that's the setup. That's the first part of the setup. We're good with that. The second part of the setup is to analyze the physics. Let's see. How should I analyze my physics? All right, so the representation, well, the concept here should be conservation of energy. Okay, so COE. Same acronym as College of Engineering. The equation for that is going to be the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. Then we need a representation. Representation for energy is a energy plot. We want to plot this. So we've got a U here, got an X here, and what the energy looks like for this is sort of a double well potential. This is a double well potential. Looks a little bit like that. Double well potentials show up all the time. They show up in magnetism, for example. So if you care about the energy related to the specific configuration of the magnetization in a magnet, this is basically what it looks like. You have that double well potential anytime you have an order parameter. And that's what we'd been looking at earlier. So we said we had something like an order parameter here. Actually, it doesn't have to be a double well parameter, but double well, to do this, you can have a single well that changes and stuff like that. I thought about trying to give you a problem like that. Let's see. So here, this was our separation, and this was X. So when you have a double well parameter, a double well potential, for something that changes, for example, with the separation, this S, this separation is, let's see, this separation is driving the equilibria. And like now it's a little bit easier to see. This guy here is your unstable, your dashed line, and this solid line is your stable equilibria. So each line along here, physically you can only have one separation. So each line along here, that dashed line there, that tells you that like right here you only have one equilibrium point and it's stable. And here you have two stable equilibria, excuse me. and one unstable equilibrium right here in the center. All right, and the arrows tell you which way you go. If you happen to be in here, you'll move up along this line. Right, if you're right here, you'll move up along this line, away from the unstable to the stable equilibrium. This x is called an order parameter, and that quantifies more or less how much order there is in the system. So, like I said, you could use this in magnetism, that magnetization of a magnet, the polarization of the magnet is I should use only magnetization. Polarization is actually for electrodes. That is an order parameter. Another order parameter would be, say, the lattice spacing or something like that. So you can have an order parameter that has something to do with the temperature in a solid, and that's another way this shows up in physics and engineering. Okay, so that gets me done with my analysis of the physics. What next? All right, oops. All right, so, I put extra things in this one, didn't I? I'm not sure if that's a great idea. Okay. Now I need my plan. That's what's next. I've got my tracking symbols down here to use. So that's a useful thing. So try to keep that in mind. So what I'd like to do is I'd like to find V. So I've got to start by finding V. And as far as energy is concerned, you should use the definition of kinetic energy because V is in that kinetic energy. That's where it's going to show up, in this initial kinetic energy here. So that is going to be K, which we do not know, right? We do not know that. It's one of these guys, is equal to 1/2 mv squared, the definition of kinetic energy. Let's see, what is that? The m I know, so that gets the little box, and the v squared is what I'm looking for. Very nice. So that's where we start. Next, we have to find that k. So how are we going to find that k? Well, we'll find the kinetic energy with, what should we call this thing? How about conservation of energy, right? Just this thing up here. So our first task is to find an equation, a valid equation that works for the problem that has our target variable v in it. So we did that here. Now we only have one question mark. That means that k is the new target, right? Our task, once we have an equation for v, is to use the new target to somehow get to our concept. So we have to use the concept in the plan somewhere. Otherwise, it's not the concept of the problem, right? You can't have a main concept of a problem that you don't use in the problem. I hope that seems reasonable to some of you. So we'll have that k plus u at that initial spot, which is x plus, is equal to the kinetic energy when it gets over, when it's right here, right? The thing is that if we want the minimum speed to get to the other side, that's that energy. That is our total energy right here, which means that all of the energy is going to be in the potential energy at this spot here. So we can get rid of any other kinetic energy there and just use the potential energy there at x0, or what we will later call 0. But we're pretending we don't know yet. Okay, so 3, we have to do something with this u, right? we don't know anything about the u, and we're going to have to find the u in two situations with x0 and x1. So let's go ahead and find u with the spring potential energy. So we've got u. We've got two springs. So we'll multiply whatever we're going to get by 2. I'll use square brackets. Then what? Okay, so I've got two square brackets. The potential energy of a spring, which you will remember is 1/2 k times x squared. But x is the difference between the x position here and the equilibrium, or not that, it's the current length of the spring and the equilibrium length of the spring. Okay, equilibrium length of the spring is L. This guy here is however far off you are squared plus, we've got a separation S, but from the wall to the rail it's S over 2, so S squared over 4. There, we're using the Pythagorean theorem. That's the current length of the spring. So the potential energy is square root x squared plus s squared over 4. So that's the current length minus the equilibrium length squared. All right, and then we get our bracket here. And this is why this is a little bit easier with energy than with forces. With forces, what you'd have to do is you'd have to figure out what the angle was at different spots and then take, the right component and stuff like that, because the force is a vector. The beauty about energy is it's no longer a vector, right? So it's just simpler to do a lot of things. All right, so what was I doing? I was looking for the u. I know what 2 is. I also know what 2 is, but I don't have to tell you because I just assume everybody knows I know what a number is. The x here, I will put a little x by. Maybe I could do I think x is better. I think I did something different, but we'll see. I think putting an x there is a little bit better because we're going to take the derivative later and it'll go away. We just need to find this x0 and x plus. And the equilibrium length is something we're given. So, let me see. Then I need to find the only thing left, right? So I found k. Here I had the choice between the u's, which I got rid of, and the x's. The x's now I have to find. So I need to find x critical with the definition of an equilibria. X critical is one of x plus, x0, and x minus, the three equilibrium positions that we have for this particular case. So this is the definition of an equilibrium, du dv, or du dx, excuse me, at the critical spot is equal to 0. I don't know. Hopefully the writing here is a little bit better than last time. I was trying to write with the thing up whatever this thing is, the tablet, in a sort of tent position. And this time I'm just letting it rest on my knee. Neither is optimal. I don't know what optimal is. Well, optimal would be I'd get one of these giant touchscreen TVs, or giant touch screens and do it on there so I could write at a normal size. Let's see. So that seems to be it, right? We wanted U. Oh no, we already have U, so that's a check mark. We wanted XC. We wanted both X plus and X naught. So I got both of those in that one. So I'll give it 2 arrows because it does all that for me. And so this is pretty much what I said. I decided that should be an X instead. But who really knows? So now that I've got that, I want to do the execution, right? So I want to use these 4 equations to get the answer. So this is a little more mathy than usual because we have to take a derivative, and so forth. The first thing we have to do is we have to substitute 3 into 4 so we can take that derivative. All right, so that means I'm taking the derivative du dx of 2 times 1/2 is 1, so it's just k times the square root of x squared plus s squared over 4 minus L, the whole thing squared. Okay, that's not really that hard, but you might not be used to it. It requires chain rules and things. Let me see, I can go back and write it again. So I want ddx of k times the square root of x squared plus s squared over 4 minus L squared. And I want to just do that for you. So let's see, what's the first thing we do? We come through here, pull out the k, right? And then we take the derivative of this part here squared, which is this part, x squared plus s squared over 4. Make sure that looks like a plus. Minus L times the derivative of this thing with respect to x. So ddx of the square root of x squared plus s squared over 4. Can I get all the way out there? I can, minus L. This, yeah, it doesn't even cut me off there. Awesome. So I've got this, and I now have to take the derivative of this part. Actually, I guess there was a 2 there because I took the derivative of x squared. That won't last long. I've got 2 parts to this next derivative. The second part is the derivative with respect to L, which is a constant, so that's going to go away. The first part is going to give me give me 1/2 times 1 over the square root. So that 1/2 is going to get rid of that 2. And then in the numerator, I'll have the x squared plus s squared over 4 minus L. In the denominator, I'll just have the square root of x squared plus s squared over 4. And that'll then be one more chain rule, which is ddx of whatever's on the inside of that square root, which is x squared plus s squared over 4, right? Now when we take this derivative, this next derivative, again we have a constant, the s squared over 4. So we have to take the derivative of x squared, so that's going to give us 2k times the square root of x squared plus s squared over 4 minus L times x all over the square root of x squared plus s squared minus over 4. So now we've got a whole bunch of stuff that we can set equal to 0. Oops. All right. And if all that stuff is equal to 0 right there. So now we need to perform that derivative, which I just did. So we're going to perform A. This should be A and this should be B. Just to make these things. Let's see, 3 and 4 I've used. A I just used when I found that this whole thing was 2k times square root of x squared plus s squared over 4 minus L over the square root of x squared plus s squared over 4, and that's equal to 0. Okay, so I've performed that. Oh no, I forgot my x. All right. And then C, what we need to do is we need to solve for xc. We're going to solve b, so we can get rid of that. So xc is then equal to the places where x is equal to 0, which is just 0, and the place where x squared plus s squared over 4 minus L is equal to 0. So what would that be? That would be x squared is equal to L squared minus S squared over 4. So that's plus or minus, right? So we have x squared plus S squared over 4 equals L squared. So we want to solve for this, so we just have to subtract the S squared over 4 from both sides. So that means that either the positive or negative version of L squared minus S squared over 4 will do. And that's really just the x component, right? In the that's really just the x component when this is unstretched, when the springs are unstretched. Okay, so now that we've done that, we want to find these two guys here. So we're going to substitute back into 3 to find u of 0, or x0, is equal to, okay, so if x is 0, then we just have k times, let's see, the square root of s squared over 4, right? X is 0, so we have the square root of x squared over 4, which is just s over 2. So we have L s over 2 squared. All right, and I'll do it that way. L minus s over 2. I can flip them around if I want because it's squared. But I'll do it that way because that's a positive number. And then we have the other u is equal to 0, right? So with the other u, when this is L squared minus S squared over 4, then we plug this in here. We have x squared is equal to L squared minus S squared over 4. We add minus S squared over 4 to plus S squared over 4. That's a square root of L minus L. That's 0, so we have u equals 0. So that actually makes things nice. We don't have two funny numbers like you do in your homework problem. Okay, so now what I need to do is I need to do what? I need to plug these guys into 2, right? I press the... That's what happens if I touch the screen. So we need to substitute d into 2. So, and let's go ahead and put 1 as well in there. So we have 1/2 mv squared plus this, which is 0, is equal to this thing, which is k L minus s over 2 squared. Well, that's kind of nice because we have two things that are squared. So that's going to make the square root easy in f, right? Because f we want to solve for, going to solve e for v, which is just multiplying both sides by 2 over m and taking the square root. So v is equal to 2k over m, square rooted. And then we have the square root of L minus s over 2 squared. So the square root of a square is just the thing itself. And so that v there is my answer. Pretty good. I think we're all happy with that one. That makes us happy. It seems sort of reasonable. It's a little weird, right? Because we've got this L minus s over 2, and it's not directly related to something geometrical. But it's pretty nice anyway, I think. So now that we've got that, here's the answer, a little prettier. And then we have to go on and check that answer. So what's going to happen when, I don't know how long it takes this thing to actually do something. So I don't know if it took the swipe. It's actually, it takes a second. Oop. Okay, well, okay, there's where it was supposed to go. All right. So that's the answer. When we're doing our check, we're checking the answer, right? We're not checking our process, we're checking our answer, right? I assume that you're checking your process as you go, right? So one of the big problems I had originally when I was doing this is somebody would give me the wrong answer and would just say, I did all the steps right, so it's obviously right. That's not the point of this. The point of this is to give you an idea about whether or not what you're actually doing makes sense, right? Or whether your final answer makes sense. Because that's one of the ways you can tell if you've gone wrong. And you should be actually doing this as you go along, if you can, while you're going along. And hopefully you will pick that up in the future, because it will mean that you'll make a whole lot fewer critical errors in the future. All right, so what does this thing do? Oh, don't press buttons you don't know what they do. Am I recording? Yes, I'm still recording. Good. There's a button on my pen. I don't know what it does, but it did something funny. Let's see. So we need the symbols. So let's see. We've got K. Come up here. K is right there. So K is a given. All right. And we've got M. M is up here. So M is given. L. L is given. And S is given. So all we're doing is making sure that the symbols in this part of the problem are things we know, right? And there are two ways we can know them. One is they're given up here. The other is it could be gravity or the density of water and so on. That we can just look up. So we can just assume we know what the gravitational acceleration is, the universal gravitational constant is, the density of water. They're just things we can look up. It's okay. We don't need to write those out at the beginning because they're things that we know. And sometimes they'll show up when you don't expect them at the beginning. So you shouldn't just know that it's likely that they'll show up. So at least as far as the symbols are concerned, everything's okay. Now we need to look at the dimensions. So, oops, too much of this. The nice thing about when I had this in the tent form is that it would just, that's exactly how long it took to swipe. As soon as I went to the, said oops, I swiped back, and it took that long to go back. So, yeah, when I had it on the tent form, I have a keyboard on this tablet that I can move things around, but I can't in this format. All right, so what do we want? We want a velocity. That's Lt to the minus 1, as it has been for several weeks. I can't promise it won't change. Then we have to take this to try to figure out if its dimensions are correct. If they match, we want the dimensions to match. So we have the square root of k over m in there. And then we have L minus S over 2. I'll keep the S. L and S have the same dimensions, so this is dimensionally homogeneous. You should check to make sure anything that's added or subtracted or so forth is dimensionally homogeneous. So then we look at this guy and we say, okay, we've got the square root of k over m, so that means we have k to the minus 1/2, and, or to the 1/2, excuse me, and m to the minus 1/2, and L, or S, excuse me, and that gives me K is kilograms per second squared. So the square root of that is 1/2 a mass and 1 inverse second. And we multiply that by an inverse half mass. And then we have a length. And so that is, these guys cancel. We have a positive length and a negative time. And so we have these two things being the same. So the dimensions are good. The dimensions are homogeneous, right? We want a dimensionally homogeneous equation when we do these things. So that was good. Ooh, I got a little timer there. So everything looks perfectly good. So that part's good as well. Last thing we have to do is check to see, does this make sense? Is this reasonable? And so the question is if I change these things, is something going to make sense? I do not know for these guys, right? So if I think about that, why should, if the equilibrium length changes, this get higher, and therefore the speed required to go from here to here get higher? That doesn't necessarily make sense to me. However, if the spring is stiffer, right, K, if the spring is stiffer, then, this this hill in the middle here should get higher. This energy that we need to get over gets higher, so then V will get higher. So that's a good one. Okay, so if I have a stiffer spring, it takes more energy to compress it, which means I'll have to have more initial kinetic energy to go through the equilibrium here, which means that, or the barrier, to go through the barrier is what we call it. So therefore, this 2K, if K increases, if you have a stiffer spring, you need more speed in the form of kinetic energy to get over the barrier. Makes sense. And if you have more mass, then you'll require less speed because you have more speed with more, you have more mass with more energy. You have more energy with more mass, actually. Okay, see, these are the things that I'd be editing out if I was going to edit these things out. But we don't have to, right? So I think the spring stiffness is more natural, right? It's talking about the stiffness of the spring, not the mass being carried by the other guy, by the slider, by the block. So that makes for a pretty reasonable thing. This is something that I've asked you to do in your WebAssign homework. So I don't remember exactly what the thing was. Did I give you a Leonard Jones potential to do this with, so you can play around with an atom? That's always fun. So that means you're going to have to find the equilibrium positions, and you're going to have to find the energies after you found the equilibrium positions, and all sorts of fun things like that. Okay, so that sounds like it was good enough for the plague year, and hopefully you've enjoyed it as much as I have, because there's nothing more fun than spending 4 hours making slides. I will talk to you tomorrow or some other time. Bye now.